Before the C-5 Galaxy existed, the world of military airlift lived under a hard, immovable ceiling. Armies could conquer territory faster than ever before, but they could not move their power with the same speed. Tanks, heavy artillery, bridge-laying vehicles, radar stations, and missile systems were massive, indivisible machines. They were the backbone of modern warfare, yet they remained prisoners of geography. If a conflict erupted across an ocean, the United States could deploy soldiers by air, but their heaviest weapons still traveled by sea, bound to slow convoys that took weeks to arrive. Strategy was limited not by firepower or training, but by logistics. Victory depended on whether the battlefield could be reached in time. By the late 1950s, this limitation had become a strategic vulnerability. The Cold War was no longer theoretical. Nuclear weapons had compressed decision-making into minutes, not months. Regional conflicts could ignite without warning, and the ability to project overwhelming conventional force rapidly became as important as nuclear deterrence itself. The U.S. Air Force recognized a brutal truth. Airlift doctrine had not kept pace with geopolitical reality. Existing cargo aircraft could move troops efficiently, but they struggled with outsized loads. Tanks had to be disassembled. Helicopters were shipped in pieces. Entire systems were delayed simply because no aircraft on Earth was large enough to carry them whole. The largest transport aircraft of the era, such as the C-124 Globemaster II, represented remarkable engineering achievements for their time, but they were reaching the limits of what propeller-driven designs could offer. Payload capacity, range, and reliability all collided with the physics of piston engines and the structural constraints of mid-century airframes. Even early jet transports lacked the cavernous internal volume required to carry modern armored vehicles. The problem was not incremental. It was absolute. Either airlift would evolve dramatically, or military mobility would remain chained to ports and coastlines. Inside the Pentagon, planners began asking questions that bordered on the absurd. What if an aircraft could carry a fully assembled main battle tank? What if it could swallow helicopters without removing their rotors? What if an entire field hospital could be loaded, flown halfway around the world, and unloaded in hours rather than weeks? These were not design goals. They were strategic necessities. The solution would not be a bigger airplane. It would have to be an entirely new class of machine. In 1960, the U.S. Air Force issued a requirement that stunned the aerospace industry. The new aircraft would need intercontinental range, unprecedented payload capacity, and the ability to operate from relatively short runways. It would have to load and unload cargo rapidly, without relying on specialized ground equipment. The numbers alone sounded unrealistic. Over 100 tons of cargo, a cargo bay tall enough for armored vehicles, a wingspan wider than most commercial airliners of the era. This was not an evolution of existing transports. It was a leap into uncharted territory. Lockheed Aircraft Corporation, already renowned for pushing the boundaries of aviation, recognized both the danger and the opportunity. The company had built record-breaking aircraft before, but nothing approached this scale. Accepting the challenge meant risking enormous financial exposure. Failure would be catastrophic. Success would redefine air mobility forever. Lockheed said yes. At the center of this gamble stood a generation of engineers who understood that conventional thinking would not work. Every assumption about structural loads, landing gear, pressurization, and propulsion had to be reconsidered. The aircraft would be so large that traditional cargo doors would be insufficient. Ground clearance would be a constant problem. The fuselage could not simply be stretched. It would need to function like a flying warehouse. Even the act of loading cargo became a design problem that demanded radical solutions. The strategic context added urgency. The Berlin crisis, proxy wars across Asia and Africa, and the looming specter of direct confrontation with the Soviet Union created a sense that time itself was an adversary. If the United States could move its heaviest forces faster than any rival, it could deter conflicts before they escalated. Airlift was no longer support. It was power projection. The vision behind the C-5 Galaxy was not merely logistical efficiency. It was strategic dominance through mobility. The aircraft would allow the U.S. military to bypass ports, infrastructure bottlenecks, and political choke points. It could deliver decisive force directly to the interior of continents. In doing so, it would collapse distance as a meaningful barrier to military response. This vision demanded unprecedented coordination between military planners, aerospace engineers, materials scientists, and economists. The aircraft would be so expensive and complex that it required political backing at the highest levels. Congress scrutinized every projection. Critics warned that the aircraft was too big, too costly, too ambitious. Supporters argued that without it, future wars would be fought with outdated assumptions and unacceptable delays. As design studies evolved, one conclusion became unavoidable. Nothing like this aircraft had ever existed, because nothing like it had ever been attempted. The C-5 Galaxy would not simply fill a gap. It would create an entirely new category of aviation capability, a machine designed not for passengers or speed, but for the raw movement of power itself. The world before the C-5 was defined by limits. The world after it would be defined by reach. And that reach came at a cost that few fully understood when the first lines were drawn on engineering paper. The challenge facing Lockheed's engineers was not simply to make an airplane larger. Size alone would have broken every existing assumption in aeronautical design. The true problem was scale multiplied by reliability. An aircraft of this magnitude could not tolerate the margins of error accepted in smaller transports. Every structural decision, every system, every pound of weight carried consequences that cascaded across the entire machine. The C-5 Galaxy would operate at the edge of what physics, metallurgy, and economics would allow, and it would have to do so repeatedly, across decades, without catastrophic failure. The most immediate obstacle was structural integrity. A cargo bay capable of holding more than 100 tons of payload created stresses that no previous airframe had endured. The fuselage would experience extreme bending moments during takeoff, turbulence, and landing. Traditional aluminum alloys, proven in fighter jets and commercial airliners, now faced load profiles far beyond their original design envelopes. Engineers had to rethink how forces traveled through the airframe, redistributing loads across longer structural paths to avoid concentration points that could lead to fatigue cracking. The wing alone represented a monumental engineering gamble. It needed to generate enough lift to raise a fully loaded aircraft weighing more than any airplane ever built, while remaining thin enough to be aerodynamically efficient. A thicker wing would increase drag and fuel consumption. A thinner wing risked structural failure. The solution demanded advanced high-strength alloys, innovative internal spars, and a design philosophy that balanced flexibility with strength. The wing would flex visibly in flight, a behavior that alarmed observers but was essential for absorbing stress rather than resisting it rigidly. Landing gear posed another unprecedented problem. The aircraft's weight could destroy conventional runways. Concentrating that mass on a small number of wheels was unacceptable. Lockheed engineers designed a landing gear system with 28 wheels, distributing the load so the aircraft could operate from existing air bases without catastrophic pavement damage. Even so, the system had to absorb immense impact forces during landing while remaining serviceable in austere environments. This was not just landing gear. It was a mobile infrastructure solution embedded into the aircraft itself. Then there was the question of propulsion. No engine in service could deliver the thrust required with acceptable fuel efficiency. The answer lay in a new generation of high-bypass turbofan engines, which promised significantly greater thrust with lower specific fuel consumption. These engines were still relatively unproven in military transport roles. Adopting them introduced risk on multiple fronts: performance uncertainty, maintenance complexity, and long-term durability. Yet without them, the aircraft simply could not exist. Lockheed accepted the gamble. Cargo handling became an engineering discipline of its own. The aircraft was expected to load and unload massive equipment without relying on cranes or specialized ground vehicles. This requirement drove the development of the Galaxy's defining features: a nose that could hinge upward and a rear fuselage that could open, allowing straight-through loading. Designing such openings without compromising structural integrity was extraordinarily difficult. The fuselage had to behave like a pressure vessel in flight and a wide-open tunnel on the ground, switching roles seamlessly without sacrificing strength. Pressurization introduced yet another layer of complexity. The cargo bay needed to be pressurized for high-altitude flight, protecting sensitive equipment and allowing crews to operate within it. Maintaining pressure in such a vast internal volume increased the stress on fuselage skin panels and joints. Every rivet, every seam, every access panel became a potential failure point. The margin for error was unforgiving. Beyond engineering, the financial risk loomed just as large. The C-5 program was structured under a fixed-price contract, an arrangement intended to limit government exposure, but one that placed enormous risk on Lockheed itself. If costs exceeded projections, the company would absorb the losses. As technical challenges multiplied, so did expenses. Delays triggered scrutiny. Weight growth threatened performance targets. Structural issues required redesigns. Each correction pushed the program further into uncharted financial territory. Political pressure intensified as critics questioned whether the aircraft was becoming an expensive experiment rather than a practical tool. Congressional hearings examined weight overruns and schedule slips. Skeptics argued that the Galaxy was too ambitious, too complex, and too costly for its own good. Supporters countered that no transformative capability had ever been achieved without discomfort and risk. The debate was not merely about an airplane. It was about how far a nation should go to secure strategic advantage. Internally, Lockheed faced an existential threat. The company committed vast resources, both financial and human, to a single aircraft. Failure would not simply mean cancellation. It could destabilize the entire corporation. Engineers worked under relentless pressure, aware that compromises could not be made lightly. Every shortcut risked long-term consequences measured not just in dollars, but in lives and strategic credibility. Testing revealed both promise and vulnerability. Structural components performed admirably in some areas and alarmingly in others. Weight crept upward as reinforcements were added. Engineers fought a constant battle between strength and mass, shaving pounds wherever possible while reinforcing critical sections. The aircraft was becoming a study in controlled excess, massive where it had to be, minimal where it could be. What made the challenge truly unprecedented was that no fallback option existed. If the C-5 failed, there was no alternative aircraft waiting in the wings to fill its role. The requirement was too extreme, the design space too narrow. Success demanded that theory, materials science, manufacturing, and operational doctrine all converge without precedent. As the aircraft moved closer to completion, it became clear that the Galaxy was no longer just a machine. It was a statement of intent. It embodied a belief that engineering could bend logistical reality to strategic will. But belief alone could not keep an aircraft aloft. Only execution could. The risk was now irreversible. The only remaining question was whether the gamble would produce a revolution or a cautionary tale. And the answer would come the moment the Galaxy left the ground for the first time. The moment the C-5 Galaxy emerged from the hangar, it was immediately clear that aviation had crossed a threshold from which there would be no return. The aircraft did not resemble an evolution of existing transports. It looked like an entirely new species. Its towering vertical tail, cavernous fuselage, and immense wingspan dwarfed everything around it. Ground crews appeared small beneath it, emphasizing the scale of what had been built. This was not merely the rollout of a new aircraft. It was the physical manifestation of an idea that many believed could not be realized. When the Galaxy took to the air for the first time, the event carried weight far beyond a standard test flight. Engineers, military planners, and political observers understood that this was a referendum on years of risk-taking and billions of dollars of investment. The aircraft lifted off not with elegance, but with undeniable authority. Its massive wings flexed under load, behaving exactly as designed, absorbing forces rather than resisting them. Against expectations, the aircraft climbed steadily, stable, and controllable, confirming that the fundamental aerodynamic assumptions had been correct. The immediate numbers were staggering. The C-5 could carry more cargo than any aircraft in history, eclipsing previous airlifters by a margin so large that comparisons felt almost irrelevant. Entire armored units could now be transported intact. Main battle tanks, once restricted to ships and rail, could be flown across continents in a single mission. Helicopters could be loaded without dismantling their rotors. Missile systems, radar arrays, and oversized engineering equipment fit within its pressurized cargo bay with room to spare. Range transformed strategy just as dramatically as payload. The Galaxy could fly intercontinental distances without refueling, connecting the industrial base of the United States directly to forward operating theaters around the world. With aerial refueling, its reach extended even further, turning the globe into a single, continuous operational space. Time, once the enemy of logistics, was suddenly compressed. What had taken weeks could now be accomplished in days, sometimes hours. The aircraft's loading system proved to be just as revolutionary as its raw capacity. The ability to open both the nose and the rear of the fuselage created a drive-through cargo bay, allowing vehicles to be loaded and unloaded rapidly. This capability dramatically reduced ground time and eliminated reliance on specialized infrastructure. In practical terms, it meant that the C-5 could operate in environments where ports were unavailable or compromised, delivering critical equipment directly to austere airfields. From the moment it entered service, the Galaxy redefined expectations. Military planners no longer asked whether heavy equipment could be deployed by air. They assumed it could. Operational doctrine shifted accordingly. Rapid deployment forces became truly rapid, backed by the certainty that their most powerful assets could follow immediately. The aircraft did not merely support strategy. It enabled strategies that had previously been impossible. The cost of this capability was immense, and it remained a point of controversy. The Galaxy was expensive to build, expensive to maintain, and complex to operate. Yet when measured against what it delivered, the equation changed. The aircraft was not replacing ships or railroads. It was filling a gap that no other system could address. In scenarios where speed determined outcomes, the value of immediate heavy lift outweighed its financial burden. Early operational missions validated the concept. The C-5 demonstrated that it could carry out sized loads safely and repeatedly, proving that its design was not just theoretically sound, but operationally viable. Maintenance challenges persisted, and early structural issues required attention, but none undermined the core premise. The aircraft could do what it was designed to do, and nothing else could do it as well. The psychological impact was equally significant. Allies saw the Galaxy as reassurance that support could arrive quickly and decisively. Adversaries saw it as a symbol of unmatched logistical reach. The aircraft projected power without firing a shot, simply by existing and being ready to move. In the calculus of deterrence, that capability mattered. Within the aerospace community, the C-5's success forced a reassessment of what was possible. Engineers who had once argued that such an aircraft was impractical now studied it as a benchmark. The Galaxy demonstrated that extreme requirements could be met if design philosophy was willing to abandon conservative assumptions. It showed that flexibility, redundancy, and scale could coexist within a single airframe. The experience of flying the Galaxy further underscored its uniqueness. Pilots described an aircraft that responded deliberately rather than aggressively, stable and predictable despite its mass. Systems were designed with redundancy at every level, reflecting the understanding that failures in such a large aircraft could not be tolerated. The Galaxy was not fast compared to fighters, nor sleek like commercial jets, but it was dependable, and that reliability became its defining trait. As the aircraft integrated into global operations, its influence extended beyond military use. Humanitarian missions began to leverage its unmatched capacity. Disaster relief efforts benefited from the ability to deliver heavy equipment, medical facilities, and large quantities of aid in a single sortie. The Galaxy became not only a tool of war, but an instrument of response when infrastructure collapsed and time was critical. In redefining what airlift could accomplish, the C-5 also reshaped expectations for future designs. No longer was air transport constrained to light and medium loads. The idea that anything too large for air transport must travel by sea was quietly retired. The paradigm had shifted. The birth of the Galaxy marked the moment when logistics caught up with ambition. Strategy, once limited by the speed of ships and the capacity of ports, now moved at the speed of jet engines. The aircraft did not eliminate logistical challenges, but it fundamentally altered their nature. Distance became manageable, scale became negotiable. Yet even as the Galaxy proved its worth, it was clear that its story was not finished. The aircraft would evolve, adapt, and influenced generations of designs that followed. Its true legacy would be measured not just in missions flown, but in the doors it opened for what aviation could achieve next. And that legacy would only grow with time. As the C-5 Galaxy settled into operational service, reality imposed its own demands on the original design. The aircraft had proven that its core concept was sound, but sustaining such an unprecedented machine over decades required adaptation. Early structural fatigue issues, particularly in the wings, revealed the consequences of pushing materials to their limits. These were not failures of vision, but reminders that engineering at the edge of possibility requires continuous refinement. The response was not retreat, but evolution. Reinforcement programs strengthened critical structural components, extending the aircraft's service life far beyond original expectations. These upgrades were not superficial. They involved deep structural modifications, redesigning load paths, and improving durability without compromising payload capacity. The Galaxy was becoming something rare in aviation, a platform capable of meaningful transformation without losing its original identity. Avionics followed a similar path. The earliest C-5s were products of an analog era, filled with gauges, dials, and systems that demanded large crews and extensive manual oversight. As digital technology matured, the Galaxy absorbed it. Modern navigation systems, improved flight management computers, and enhanced situational awareness tools transformed how the aircraft was flown. Crew workload decreased. Reliability increased. The aircraft became safer, more efficient, and more compatible with evolving global airspace requirements. Perhaps the most significant evolution came with propulsion. Advances in engine technology offered opportunities to dramatically improve performance and efficiency. Newer engines delivered greater thrust with reduced fuel consumption, extending range and increasing payload margins. These upgrades did more than save money. They expanded operational flexibility, allowing the Galaxy to operate more effectively in hot, high-altitude environments where performance margins were historically thin. Through these changes, the aircraft retained its defining characteristic: unmatched internal volume. No redesign ever compromised the cavernous cargo bay that made the Galaxy indispensable. This continuity ensured that equipment designed decades later would still fit within an airframe conceived in the early Cold War. In an era where rapid technological turnover often renders platforms obsolete, the Galaxy demonstrated the power of designing for excess capacity from the outset. The influence of the C-5 extended far beyond its own fleet. It reshaped how engineers approached large aircraft design. The idea that structural flexibility could be an asset rather than a liability became more widely accepted. The use of distributed landing gear systems informed future heavy transports. Cargo handling concepts pioneered by the Galaxy appeared, refined, and adapted in later designs. Even commercial aviation absorbed lessons from the Galaxy's approach to redundancy and durability. Operationally, the aircraft became a constant presence in global events. It supported military deployments, sustained long-term operations, and responded to crises where speed and capacity mattered more than anything else. Its silhouette became familiar on runways across the world, a quiet indicator that something large and consequential was underway. Unlike fighters or bombers, the Galaxy rarely appeared in headlines, yet its absence would have been immediately felt. Culturally, the aircraft achieved an unusual status. It inspired awe not through speed or aggression, but through sheer scale and purpose. Aircrew spoke of it with a mixture of respect and humility, aware that they were operating one of the most complex machines ever to fly. Ground crews understood that maintaining it required discipline and precision, because the margin for complacency simply did not exist at this scale. The Galaxy also influenced strategic thinking. It reinforced the principle that logistics is not a secondary consideration, but a central pillar of power. Nations observed how the ability to move heavy assets rapidly changed the dynamics of deterrence and response. The aircraft became a case study in how engineering choices ripple outward into doctrine, diplomacy, and global stability. Over time, newer airlifters entered service, optimized for different roles and efficiencies. Yet none replaced the Galaxy outright. Its niche remained uniquely its own. When cargo was too large, too heavy, or too critical to delay, the solution remained the same. The Galaxy would fly. This endurance underscored a deeper truth about its design philosophy. The aircraft was not optimized for a single moment in history. It was built to outlast assumptions. By anticipating growth, uncertainty, and change, its designers created a platform resilient to shifting requirements. The Galaxy did not merely survive modernization, it thrived because of it. As decades passed, the aircraft transitioned from revolutionary newcomer to venerable cornerstone. Its continued relevance became a testament to the foresight embedded in its original design. In a field where obsolescence is often measured in years, the Galaxy operated on a different timeline altogether. The legacy of the C-5 is not confined to its missions or its statistics. It lives in the way engineers think about scale, in the way strategists think about reach, and in the way aviation history measures ambition. It stands as proof that when design dares to exceed immediate needs, it can shape possibilities for generations. And yet, for all its technical achievements and strategic influence, the Galaxy's story ultimately points beyond itself toward a broader lesson about the relationship between human ambition and the machines built to serve it. In the end, the C-5 Galaxy is best understood not as an aircraft, but as an argument made of aluminum, steel, and jet fuel. It argues that limitations are often temporary, imposed less by physics than by caution. It argues that logistics, long treated as a constraint, can be transformed into an instrument of strategy. And it argues that ambition, when matched with disciplined engineering, can permanently alter the balance between what is imagined and what is possible. The Galaxy emerged from a moment in history defined by uncertainty and urgency. The Cold War demanded answers to questions that had never been asked before. How fast could power be moved? How far could it reach? How much could be delivered, intact and ready, without waiting for ports, railways, or political permission? The C-5 did not answer these questions incrementally. It answered them absolutely. Its greatest achievement was not merely lifting unprecedented weight into the air. It was collapsing distance as a meaningful barrier to action. By making the movement of heavy force routine rather than exceptional, the Galaxy reshaped how planners thought about response time, deterrence, and global responsibility. The world became smaller not because geography changed, but because access did. The aircraft's long service life reinforces a truth often overlooked in technological history. True breakthroughs are rarely perfect at birth. They require patience, adaptation, and the willingness to invest beyond initial success. The Galaxy's early challenges did not diminish its importance. They strengthened it. Each upgrade, each reinforcement, each modernization extended not just its lifespan, but the relevance of the original idea behind it. There is also a quieter lesson embedded in the Galaxy's story. While fighters and bombers capture attention through speed and power, it is airlift that sustains reality. No operation, military or humanitarian, functions without the ability to move people, equipment, and hope itself. The Galaxy operates in that space where outcomes are decided long before headlines appear. When disaster strikes, the aircraft's cavernous interior becomes a lifeline. When conflict looms, it becomes a signal that support will not be delayed. In both roles, it demonstrates that engineering excellence is not only about performance, but about reliability under pressure. The Galaxy does not promise elegance. It promises presence. Its legacy also lives in the confidence it gave future engineers. By proving that extreme requirements could be met, it expanded the boundaries of acceptable risk in design. It encouraged a generation of aerospace professionals to ask not whether something was too large or too ambitious, but whether it was necessary. That shift in mindset continues to influence aviation long after the Galaxy's first flight. Looking back, it becomes clear that the C-5 Galaxy was never about excess for its own sake. Its size was a response to reality, not a display of indulgence. Every ton of payload, every meter of wingspan, every redundant system served a purpose rooted in strategic need. The aircraft was as large as it had to be, and no larger. As long as there are missions that demand speed over oceans and capacity beyond compromise, the Galaxy's relevance endures. It stands as a reminder that the most transformative machines are often those built not for spectacle, but for necessity. Machines that quietly rewrite what can be done, then do it again, mission after mission, year after year. In the arc of aviation history, the C-5 Galaxy occupies a singular position. It is the bridge between ambition and execution, between strategy and reality. It is proof that when human will aligns with engineering discipline, the limits of the possible shift outward. The history of aviation is written not only in speed records and altitude milestones, but in the machines that carry the weight of consequence. It is written in steel that flexes rather than breaks, in engines that endure rather than impress, and in designs that accept risk in pursuit of capability. The C-5 Galaxy embodies that truth. The history of aviation is written with steel, ingenuity, and the will to challenge limits.